Today's lesson, uniform circular motion. So when objects move in a uniform circle, so we're specifically talking about circles and we're talking about uniformity. And we have this very, very important word here called speed. A speed of an object that's moving in a circular motion that's uniform, their speed is constant. It is February 28th. Forgot what year it was for a second. No, your acceleration is not constant. Speed is equal to our distance divided by time, as was so conveniently left on the board from Levins this morning. This is our simplest formula, the first formula we ever learned, but we're looking at a circle. So what is the distance around a circle better known as? Circumference. So the circumference of the circle is the distance the object travels. What do we normally call the time to go all the way around a circle? Think of your waves chapter from last year. Period. One full loop. One loop is one period. So we have a formula that's not just d over t. Right? Let me just undo this. I don't want that there. No, but we have a velocity formula. Okay, so the velocity will now equal, what is the circumference formula? That is 2 times pi times the radius. That's the area of a circle, and we do not care about that currently. What symbol do we normally use for period? Big T. Specifically big T and not little t, just for showing it's for one loop, not just the elapsed time of it spinning, the time for one loop. So it's like a wave. So we have our new formula for the speed of an object in a circle. The distance around the circle divided by the time it takes to go around the circle. So this allows us to do a little bit of math. If we know the speed, we can measure the radius. If we know the time, we can measure the radius and other such things. Now, the speed of this object is constant. What is not constant is the velocity.
Interesting choice.
How does that work?
Guys, can I get this one?
Dante, give us a...
Really embarrassing, so I kind of don't want it.
Let's do it.
Is it because speed is scalar and velocity is vector, and it's kind of like since going around a circle, it's like changing a little bit?
It's changing the direction constantly. So the reason the velocity is changing is because its direction is changing. Its speed is constant, but its direction is constantly changing around the circle. And so it has an acceleration. So there is acceleration in this particular object because the velocity is not constant. Acceleration, remember from the old definition, is the change in velocity with respect to time. So how the velocity changes is an acceleration. This is a specific name. It's called centripetal acceleration. Centripetal or centripetal, depending on how you want to pronounce it, acceleration.
I love centipedes. Favorite animal.
That was a good one. I like that. Centipedes is good. Hadn't heard that. I like that. Okay. So, yeah, I think I'm just going to give you this formula. I don't think I'm going to explain why it exists.
Okay, cool.
So the formula is the acceleration centripetal. The A little c for centripetal acceleration is v squared divided by r. And I don't know why it's written like that, but that's fine. It is. It's true. It's real. It definitely does. I've done this at least 4 times. So this is absolutely true. I don't know why it's not derived, but that's fine. We don't need to derive every single formula we use. We can just accept things every once in a while. Say, it's the formula. Like, fine, let's move on. All right. I got all this space, so I'm going to draw a circle. If this is the object's movement, I don't want to write that in there. Undo. You didn't draw a pretty circle? I didn't even cheat.
Yeah, that's why yours looks bad.
It looks... Okay. Which direction is the velocity going?
Every.
Well, let's pick a spot. Let's say undo. Don't erase the. It's tangential, which is a great word. It's a tangent line. So if I'm looking at the very top, I can say the velocity is that way. Tangential velocity. Great words. And it's always tangential to the circle's path. The velocity is constantly changing. So which direction is the acceleration going?
Always forward from the center.
No.
Every direction.
It's going in every direction all at once. Does that help us?
No.
No. Okay. Let's say I'm going in this around the circle with this speed. What direction am I going to turn?
Down.
Down. So that's the direction of the acceleration. The acceleration is here. I didn't mean to jump it in like that, but that's where the acceleration term is. Because this is what will turn it. So yes, it's literally what I was about to write down. AC always points to the middle. I should write center though. Center.
You're saying it's always down.
It's not always down.
But like down is in like if you think of down on Earth, it's like towards the middle.
Yeah, but down means towards the center. That's what down means on Earth.
So I said down.
But like, if you're over here on the circle, it's an up on this diagram.
But it's still like down.
No.
No, that's up.
Go like this. I don't think down.
It's like if I was like in Australia.
Okay, so two things that are a problem. Currently, most of what we're going to work with today are horizontal circles, spinning around like this. So the acceleration is towards the center of the circle, not down, right? If you're in a horizontal circle, the acceleration of the circle is towards the center of the circle, not down. No. Back to the lesson. Using Newton's laws, we can put a force into this. Because they're an acceleration, there's a push on this object. There has to be some kind of force making it turn. And so we can calculate how many newtons that force is. Because there's a force, pen back on. A force acting towards the center.
Is this perchance centrifugal force?
Yes, that's kind of. No. Centripetal force, actually. Yeah, it's different. I'll explain later.
We already used the word centrifugal.
Yeah, but the centripetal acceleration matches the centripetal force. So Fc for centripetal force is in what direction? Center. To the center. What's Newton's second law? Wow, it is definitely last block today, isn't it? Nope.
Wait, which one?
Two.
Object in motion stays in motion unless that's like.
That's one. That's number one. What's number two? MA is right.
Gravity.
In this case, we're going to use AC because that's what we're looking for.
What's the difference between centripetal and centrifugal?
They're opposites of each other.
Oh, centrifugal.
It's a reaction force, like a normal force and a gravity force. Yes, that's the best way to describe it.
That's cool.
So we know these two things. Velocity is equal to 2 pi r over t. And I know the acceleration is, what's it called? V squared over r. So the force C is equal to m v squared over r.
Makes sense.
Because AC, like this, is just, that's just this. They're the same.
Nice.
That's it. Very exciting. Now we have one more force equation.
Wait, do we have to switch up velocity to?
So next thing we're going to do, as Jacob so kindly suggested,
Thanks, Jacob.
we're going to take this velocity term and put it into there. Now, we can do this with algebra, or I could show you the answer.
Trust the answer.
Algebra.
Don't- Of course. It's just a formula. We're just deriving the formula.
Just skip to the end.
skip to the end, which I agree.
Oh no, it must be squared. Somewhere.
4 pi squared rm over t squared. Isn't it awful?
Wait, why does the R switch to the top?
Because I have, good question, why does this r seem to move to the top? Because I put 2 r's on the top. So I'm left with 1 r on the top.
Let me just.
Because this whole term gets squared first. I could show you the algebra, but it's a lot of algebra for no reason. It's not that bad. I know.
Is this on our formula?
Yes, it is. This is why I put 4 columns on your formula sheet. There's a lot of formulas on it. There's a lot of them. So this is all in the middle. All of these formulas are showing up in the middle of your formula. Oh, yeah, everything there. It's all in there.
What?
That's most of it. This is the theory chunk. Any questions? Let's try example 1. Calculate the centripetal force acting on a 1.5 kilogram object, whirling at a speed of 2.3. Yeah, whirling. At a speed, not a velocity, a speed of 2.3 meters per second in a horizontal circle that has a radius of 0.6 meters. A nice, straightforward, plug it in kind of question. And I want the centripetal force. So, force, centripetal. Whoops, pen on. Force, centripetal, is mv squared over r. And I'm using this one because it makes more sense. I have a mass, a velocity, and a radius. So I'm going to use this one. The mass is 1.5 times 2.3 squared divided by 0.60. That's the entire question. And now it's just an exercise in typing all of those buttons into your calculator. I will shortcut us a little bit and just get right to the answer. It's 13,225, bunch of numbers, which will round to just straight 13 because we have 2 significant digits. 13 newtons of centripetal force. And as I hinted at, we like to say centrifugal force, but that's our opposite.
Are they centrifugal newtons?
Hmm?
Are they centrifugal newtons too?
Well, no, it's just a force.
What are you thinking?
It would be. So the best way to try to think about it is the 13 newtons is what force is making it turn into a circle. Right? And then the centrifugal force that you would feel is being pulled outward. Like when you're in a turn, you feel force to the out of the circle. That's your centrifugal force. It's the opposite.
And that just like exists. Just like I get that it's a reaction force.
It is just a reaction force. It's just a Newton's third law reaction force. It's the same way we do this here. We feel the ground pushing up on us because gravity is pulling us down. We actually interact with and notice the ground holding us up. That's what we notice. Like when you walk, you feel the ground hitting your feet. You don't feel the gravity pulling you down.
If someone like hits you, that's just the wrong force.
Yes, it is. Anyways, that's the best way to turn between them. On example 2, we don't need to be at this all day. This is already probably taking longer than it should. Let's try that again. A car traveling at 14 meters per second goes around an unbanked curve, which is flat. So there's no bank to this curve. It's not a NASCAR track. The road has a radius of 96 meters. What is the centripetal acceleration? I mean, it is, yeah, but C is equal to V squared over R, which is 14 squared divided by 96. That's it. It's 2.0416, bunch of numbers, but it's 2 meters per second squared.
Oh, sorry, 2.0.
It is 2.0. It is 2 significant digits worth of information. So we have an acceleration of 2 meters per second squared towards the center of this term. This is the same way you feel in a car, right? When you turn a corner, you feel push out, right? So what's pushing in?
The centripetal force.
Yes. What is providing that centripetal force?
Probably the v squared over r.
No. What's creating this force?
Well, when I'm in a
Tires. It's the tires. The tires are creating friction on the ground. Allows you to turn. Next question. A plane makes a complete circle, a big loop of a radius 3,622 meters in 2.10 minutes. How fast is the plane? It's a big bang. It's a 3-kilometer turn.
No, but also like 2.1, and then it's minutes. You think that's like...
Yes,
minutes and one
we're not
minute.
going to do the minutes conversion though.
Yeah, 2 minutes.
We can put 2.1 in our formula. We can't put 2 minutes 6 seconds in the formula.
Oh, you could put like...
Oh, whine about it. Let's go and do the question. We're going to do the formula we want is that's an R, that's a T, and I want a V. So what formula has V, R, and T in it? V is equal to 2 pi R over T. What do I want? Oh, the speed. That's easy. Why did I make everything so easy?
Yeah, these questions were.
Thank you, Mr.
You're welcome. 3,622 and 2. Oh, right. You're right. Undo. I got to go 2.10 times 60, which is 126. Because time is always in seconds. You don't do math in minutes. Got to do it in seconds.
So you can't put 2.1 into your formula.
No, but you can multiply it by 60 first. You got me carried away. I got 181 meters per second.
181.
181.
I got 180.
Oh, yeah, but it's 180.
Rounded correctly.
No, 360.
As shown. Let's draw a diagram showing just the forces. So I'm going to draw my object here. And I'm going to draw the forces that are attached to it. What forces are happening to this particular ball? There's one going down. What do I call that one? It's gravity. Force of gravity is going straight down. What other forces are really happening to this particular object? There is a tension force. Where does the tension force go? At the angle up the rope. So there's a force of tension there, which we normally get away with just writing. Oh, I don't want to do that. Undo. Fine FT. All right. Those are the only two real forces. What component forces do we need to worry about? I have to worry about this X force and this Y force. So I'm going to cut my tension into two pieces so I can work with my X and Y coordinates. So I have my FT in the X direction and my FT in the Y direction. So those are my forces as set. So I've just have the two real forces and components of my tension force. But this allows me to do some net equations. What is the gravity equal to? No. What's the force of gravity equal to in my diagram? No. Just what is which symbol is the same as gravity? Is FT in the Y direction. Right? This force has to equal this force because it's not moving up or down. Right? It's traveling in a flat circle. So there's no up and down movement. So the up force has to equal the down force. What does FTX equal? What would that probably be analogous to? What is the FTX doing to this object's movement? It's going to be our centripetal force because it's what's making it move in the circle. It's pulling towards the center. So my FC is equal to FT in the X direction. All right, so we got to figure out a few things here. We have to figure out, and since I didn't have enough room here, I'm going to put it up over here. What is the radius of the circle? because we just need to use our trig skills to figure this out from over here. So from the diagram, how big is the radius? How would I find out? Yes. So it's 1.4 sine 32, because we can do trig. What does that equal? 0.742. I'm going to keep the 742 on it because I'm doing an estimation, so I'm keeping one extra number just for rounding error problem. So I know it's 0.742 is my radius in this case, and I just put it up there to show the math how we got that. We'll use it later. But it might be useful if I measure the other angle. What other angle do I have here? It's at 58. That'll be useful later. Why do I like that angle more than 32? No, that doesn't change much. Because it's off the horizontal. So all of my XY rules will now behave properly. And I can use that angle in all of my component math and stuff will be okay. All right. So find the speed of the ball. What formulas have speed in them that we may be able to solve?
2 pi r.
Over t, right? So that's true, but what else do we not know?
T.
We have no idea how long this is taking, so that's not going to help us. What could we find out?
mv squared over r.
Yeah, we're going to look at the mv squared over r. We're going to look at our force centripetal equation. But we have to use both. So we got to figure out what the tension in this string is first. So how do I figure out the tension in the string?
Like all the forces.
Yeah, we're going to use the sum of the forces. Which two forces should I use? The x or the y? Y. We're going to use y because we can. So I got to figure out what is Fty. That equals force of gravity, right? That's true. The up force has to equal the down force. So I'm now going to pull this apart in my formula. So I have Ft and the sine of 58 degrees is equal to the mass times the gravity. Just expanding out my terms here. So now I know what the other ones are. So Ft will be mass 0.80 multiplied by 9.8 divided by the sine of 58 degrees. And I can get a tension number. Force of tension. I think it is 924 newtons. I should probably get my calculator out and do this properly. But I do trust you guys saying I'm right, which makes me feel good. Okay, now that we have our tension force, we can now do our force centripetal. So
Ft or Fty?
this is now just full T because I used the sign on it. Yeah, we did the sign on it, so now this is just your total on the angled force. So it's right up the rope, it's 9.24. So now I can try to find Fc, which is Ft in the x direction. So this is mv squared over r, and this is Ft, the cosine of 58 degrees. This is mainly why I wanted to get the 58 out of the diagram, is because when I'm using x, I want to use cosine, and when I'm using y, I want to use sine. I don't like mixing those up. Even though you absolutely can, it's much better to not mix them up. All right, let's do a quick rearrange because I do not have space for this. I really didn't space this appropriately on our page. V is equal to what formula? Can we solve for this V all by yourself? How do I deal with that?
Square root of Ft cos r, Ft cos 58 r divided by r.
That'll do it. I mean, I'm going to put it in a different order. I'm going to go, oops, I don't want it green. I want it nice and pretty colored. R Ft cosine of 58, all divided by m, and all square rooted. So that's my formula. I do not have space to type my numbers in. I will just do it in my calculator, and I get 2.131, bunch of numbers, which will end up, because this is the final answer of a particular part, I can write it as 2.1 meters per second. That's my speed. That's how fast it's going in our circle. Very exciting. How much time for one revolution? All the way around once. Oh, how much time did it take? Like how long did we take solving it? Fair. The period of revolution. So we're looking for t. The formula with t is v is equal to 2 pi r over t. So t is equal to 2 pi r over v. And we can solve that. I know 2. I know what pi is. I know the radius is 0.742. Now we get 2.131, all the numbers that we totally saved from the previous question and didn't just put 2.1 in it.
2.2.
I got 2.187. 2.1877, bunch of numbers, which does round to 2.2.
2.22.
Really?
I didn't use 2.13.
Yeah, I used all the numbers in the back there. 2.2 seconds as my answer there. So that's that answer, even though there's this like kind of cutoff there. It's not really a great doing it. One day I will remember to resize this particular example. Today is not that day. What's the magnitude and direction of the acceleration of the ball? This is easy.
They're just like fx, and then you have to do like f.
Yeah.
Okay.
So what is... yeah, we can do it funky. We can do it basically from our starting point. I think the best way to do this is kind of easy. We can do FC is equal to MAC. It's pretty straightforward.
And we know that ftx equals MC.
That's right. So we're going to go rearrange this for AC. That is equal to FC over M, right? Which FC is FTX over M, which is FT cosine of 58 over M. So FT was 924. Cosine 58 over 0.80. Mm-hmm. 9.24. Let's do this one. Hey, I'm going to write it down here because it fits better. 6.12 0. Let's just get rid of that 2. Speed, acceleration, meters per second squared. Forgot what I was solving for there. Oh, let's fix that. Squared. Got one more. Oh, the direction. Center. Where is the acceleration going? To the center of the circle. Not down. Oh, what does it? Why? Where? The string. The string is making it go towards the middle. So, how much tension is making it go to the center? No, you don't?
Oh, no, we don't.
Oh, cool.
But it is 4.
It's 4.9, in case you were wondering. Because if you just don't just write it down, because I think that's what I was having a problem. I think you guys, you guys have more space than me. That's what happened. I took this question off your page because it's dumb.
It is pretty dumb.
Because it's just
Twice already.
FTX, but we never found it as a number. It was in numbers. It's just FTX, which is FT cosine 58, which is 4.9123, whatever.
You know what? I don't even think I need to do the exercise for this.
4.9 total. I'll finish this question up and be all done. There are snap questions, which are easy, which gets used to the formulas. It's pretty straightforward. And the point questions, which have equilibrium in them.
Where do
So
we get the snap stuff?
in the pages I have right for you here.